for loop gain analysis we have to break the loop and find the transfer function. So, we will replace this and we will make it minus a. This is your breakpoint. So, V in S, V out S. Okay. So, loop gain transfer function, and this will be what? Minus a times beta, okay, GPWM H DRVS HL CS. Now, let us replace each. What was GPWM? 1 over VM. This guy was VDD, and this was 1 over LC over this. Let us copy this and paste it. Okay. So, if I want to do the same thing again, phase and magnitude response, so that is what we need to do for stability analysis. So, LG of S magnitude what will the DC phase? Sorry, DC gain?
DC gain is A beta VDD by VM.
A beta VDD by VM. Okay. Then this is your so what will be the slope of this? You have double pole, minus 40 dB per decade. So, where will it cross 0 dB? So, what is the gain here? A beta so omega UGB equal to, so the slope is f naught over f square or omega naught over, let us write in terms of omega square, okay, multiplied by
A beta VDD.
Wait. Is this correct? We want to find the gain at omega UGB should be 1. So, omega naught over omega UGB square multiplied by A beta VDD over Vm. This should be 1. Correct? So, from here we can find the omega UGB. So, omega naught square over omega UGB equal to how much? Let us move that omega naught square. So, omega UGB square equal to omega naught square A beta VDD over Vm. Okay. Omega UGB equal to omega naught square root A beta VDD over Vm. Okay. So, if you know omega naught, and omega naught is nothing but 1 over square root LC. So, okay. So, we can find the omega UGB for this. So, the phase is already, which means obviously this is much higher than your omega naught, omega UGB, and it depends on the gain, how much gain you have, and the majority of the gain is coming from the amplifier. So, mostly that will define. So, let us say your Vm is 1, VDD is 1.8 volt or so, and beta factor may be half or 1. So, this factor won't dominate much, but A will dominate in the gain, and that basically that will make your omega UGB much higher than your resonance frequency, and your phase is already dropped close to minus 180 at omega naught. So, inherently this is what? Stable or unstable?
Unstable.
Okay. So, omega UGB is means system is inherently unstable. So, you cannot simply put the amplifier in the feedback and get the regulated output. Okay, for DC it is fine, but for AC you know it is unstable. So, inherently this is unstable system, we need to stabilize it. Okay. Need to stabilize. So, let us copy this again. So, what we will do, we will replace this amplifier with a transfer function h of let's choose a bigger okay. So, instead of amplifier I am putting a block which is H comp S. Now, if you go back here and copy this guy, so this A will be replaced by let me okay. Okay, so okay. So if I assume H comp S equal to, let us say, some gain K over S multiplied by HLCS, what would happen? Not HL multiplied, but let us say 1 over HLCS. So, that will get cancelled out. What left over is the integrator, and integrator we need because we need a very high DC gain. So, integrator has to be in the compensator. Okay. So, your HLC will cancel out and your leftover will be if I call it LG S, LG compensated S, let us call it okay. So, you have beta VDD over VM K over S. Okay. Is it possible? So, this first order system, so stable, okay, and UGB can be controlled by K. Okay. So, which means you had a complex pole. If I introduce a transfer function with the complex zeros, they will cancel each other, and what you get? It is a perfect first order stable system. But what is the problem with this? I mean, can we realize complex zeros?
But in reality, we can't make ideal integrator.
Integrator? What do you mean by ideal integrator? I mean, it's fine. If it's not ideal integrator, worst case what will happen? You won't get an infinite gain at DC, huh? But your UGB will remain same. Okay. So, whether it's a real integrator or real or ideal integrator, it should not matter. I am talking about the, this LC factor actually. As long as you cancel that out, So, we can realize complex zeros, but the problem is those you cannot exactly place at the same frequency, and it is a high Q system. So, if you are slightly off, and phase will drop quickly and it will make it unstable. So, placing a complex zero is not feasible actually. I mean, theoretically you can say, you can cancel it out, but the moment you practically implement it, you cannot match exact those LC. Those LC is mostly I mean off the chip, and you are going to realize with the active components. So, you cannot track each other in that case, because L and C may vary actually, may vary with the temperature, and they have some tolerances also. Okay, and there might be slight, and even though we have considered 1 over square root LC fixed, but if you remember, that was assumption for assuming that your R loss is much smaller compared to your R load, and that is why we get rid of. So, omega naught, but there will be slight change, and for that high Q, even that slight change may affect. So, you cannot really basically implement it and cancel the pole exactly. So, we never apply this approach for stability. So, we can cancel complex poles due to LC by introducing complex zeros in H comp S at omega naught. Okay. However, we can't practically implement complex zeros with omega naught equal to 1 over square root. So, practically this stability method is not feasible. Okay. So, how can we compensate? Any other approach? So, we cannot go with this. What could be the other option? I mean, you guys have seen stability methods in LDOs, so you should know how to do it. What was the very first stability? Dominant pole compensation. So, now we can push omega naught outside UGB and stabilize it.